How can a filter become extremely selective, passing one frequency with almost no loss, while rejecting frequencies just a little higher or lower? The answer lies in one of the most important concepts in RF engineering: resonance. In the previous lesson, we learned that RF filters are physically built using inductors and capacitors. By combining these components, engineers can create filters that shape the frequency spectrum. However, simply connecting inductors and capacitors is not enough to achieve the sharp frequency selectivity required in modern RF systems. Engineers need a mechanism that naturally favors one frequency over all others. This raises an important engineering question. How do LC circuits become highly selective and respond strongly to only one particular frequency? A resonant circuit, also called a tuned circuit, is an LC network that naturally responds most strongly at a specific frequency called the resonant frequency. At resonance, energy continuously transfers back and forth between the capacitor's electric field and the inductor's magnetic field. This efficient energy exchange creates a strong response at one frequency while reducing the response at frequencies away from resonance. The resonant frequency depends only on the values of the inductance and capacitance. By changing either component, engineers can tune the circuit to a different operating frequency. Intuitively, imagine pushing someone on a swing. If you push at exactly the right rhythm, the swing moves higher and higher with very little effort. If your timing is wrong, the swing barely moves. A resonant circuit behaves the same way. It responds most efficiently at one specific frequency. Physically, consider a radio receiver designed to receive a 100 MHz FM station. The LC resonant circuit is tuned so that it resonates at 100 MHz, allowing signals near that frequency to pass efficiently while greatly reducing signals from neighboring stations. This is one of the key principles behind channel selection in RF systems. Mathematically, the resonant frequency is determined by the inductance and capacitance of the LC circuit, F0. This equation shows that increasing either L or C lowers the resonant frequency, while decreasing them raises it. Resonant circuits are fundamental building blocks in RF filters, oscillators, impedance matching networks, and tuning circuits. They are widely used in communication receivers, transmitters, radar systems, satellite equipment, and wireless sensors. Engineers carefully select the values of inductors and capacitors to achieve the desired resonant frequency and bandwidth. In practical RF filters, multiple resonant circuits are often combined to produce sharper frequency responses and improved selectivity. Without resonance, achieving narrowband filtering in modern communication systems would be much more difficult. Understanding resonant circuits is essential because resonance is what gives many RF filters their frequency-selective behavior. It allows engineers to isolate communication channels with remarkable precision. A common misconception is that resonance amplifies signals by creating extra energy. In reality, resonance does not generate energy, it simply allows energy to transfer more efficiently at one particular frequency. In the next lesson, we'll explore the quality factor Q and learn how engineers measure the sharpness and selectivity of resonant RF filters. In this lesson, we learned how resonant circuits use inductors and capacitors to respond strongly at one specific frequency. We also discovered why resonance is the foundation of many RF filters and tuning circuits. In the next lesson, we'll explore the quality factor Q and see how it determines the sharpness of a filter's frequency response. If you found this useful, like the video, subscribe, and follow for the next lesson.